If this island's most important factories stopped tomorrow, the shock would not stay in Taiwan. Production lines in Detroit could slow. New iPhones could be delayed. AI data centers could wait for their most powerful processors. Even advanced weapons programs would face a question no military planner wants to hear. Where will the next chips come from? And while warships cross the Taiwan Strait, the world's most critical machines continue running behind clean room walls. This is not simply a story about semiconductors. It is the story of how one company became a pressure point for the entire global economy, and why America is now spending extraordinary sums to make sure the future of computing does not depend on one island. The company is TSMC, Taiwan's semiconductor manufacturing company. You may never see its logo on a phone, a laptop, or an AI server. That is exactly the point. TSMC does not need consumers to know its name. It manufactures the microscopic engines inside products sold by companies that everyone knows. Apple designs its own processors. NVIDIA designs the chips driving the AI boom. AMD and Qualcomm design silicon for computers and communications. But a design on a screen is not a working chip. It must be manufactured layer by layer with tolerances measured in atoms. For many of the world's most advanced designs, the road leads to TSMC. By 2025, the company controlled more than 70% of global foundry revenue. Advanced processes, 7 nanometers and beyond, generated nearly 3/4 of its wafer sales. These numbers do not mean TSMC makes 70% of every chip. They mean that inside the specialized business of manufacturing chips for other companies, one player has opened a lead no rival has managed to close. That lead began with an idea the industry once considered almost unnatural. In the 1980s, semiconductor companies usually designed and manufactured their own chips. Intel built Intel chips. Texas Instruments built Texas Instruments chips. Manufacturing was not a service. It was part of the company's identity. Morris Chang saw the weakness in that model. A young chip designer might have a brilliant idea, but no chance of financing a modern factory. And if it asked an established manufacturer for help, it risked handing its design to a future competitor. So when Chang founded TSMC in 1987, he offered a radical promise. We will build your chips, and we will not compete with you. That promise created the pure-play foundry. At first, it sounded like contract manufacturing, a useful but unglamorous corner of the technology business. In reality, it changed who was allowed to innovate. Companies could focus their money and talent on architecture and software, while TSMC carried the brutal cost of fabrication. The fabless chip industry exploded. Qualcomm, NVIDIA, AMD, and hundreds of smaller designers could compete without constructing factories that cost billions of dollars. TSMC was no longer just another supplier. It became the trusted manufacturing layer beneath an entire ecosystem. But trust alone cannot etch billions of transistors onto a piece of silicon. A leading-edge fab may look silent and sterile, yet it is one of the most complex production systems humans have ever built. A wafer can spend months moving through repeated cycles of deposition, exposure, etching, cleaning, inspection, and testing. Each machine must work with the next. Each chemical must be pure. Each vibration, particle, and temperature change must be controlled. The goal is not merely to produce a chip. It is to produce millions of chips with consistently high yield. That word, yield, is the hidden weapon. Two companies can own equipment capable of the same process node and still achieve very different economics. If too many chips on each wafer fail, costs explode. Customers lose time. The manufacturer loses credibility. TSMC's advantage comes from decades of process knowledge. Millions of small corrections learned through relentless production. Money can buy machines. It cannot instantly buy 30 years of accumulated manufacturing judgment. Then artificial intelligence changed the value of that judgment. The AI boom is often described as a race between models. OpenAI against Google, American labs against Chinese labs, one chatbot against another. Underneath that software contest is a physical race for computation. Training and running advanced models requires enormous fleets of accelerators. NVIDIA may design the most famous AI chips, but those designs still depend on manufacturing and advanced packaging. In other words, the AI revolution has a factory floor. TSMC's role now extends beyond printing smaller transistors. Modern AI systems increasingly depend on advanced packaging, placing multiple pieces of silicon close together so they can exchange data at extraordinary speed. The bottleneck is not only how many processors can be designed, it is how many complete, usable systems can be manufactured and packaged. That helps explain why TSMC's importance rose so quickly. The company stands where three powerful trends collide. Smartphones still need leading-edge efficiency, AI demands extreme performance, and governments now treat chips as strategic infrastructure. The result is a paradox. The world built an efficient semiconductor system by concentrating each difficult task among a few specialists. American firms became dominant in chip design and key manufacturing equipment. A Dutch company became essential to advanced lithography. Japanese firms mastered critical materials. Taiwan became the center of foundry manufacturing. The system is efficient because no country does everything. It is fragile for the same reason. A chip may cross international borders dozens of times before reaching a finished device. One disruption can travel through the network like a shock wave. The pandemic offered a preview. A shortage of relatively ordinary automotive chips forced factories to slow or stop, even though the missing component cost far less than the vehicles waiting for them. Now imagine a disruption at the leading edge. Congressional researchers have estimated that almost 90% of high-volume leading-edge production has been concentrated in Taiwan. The exact percentage changes as new fabs open, but the strategic fact remains. Much of the world's most advanced computing capacity is clustered on an island facing earthquakes, water constraints, power risks, and a deepening geopolitical confrontation. This does not mean conflict is inevitable. It means the consequences of miscalculation are unusually high. The Taiwan Strait is one of the world's busiest and most closely watched waterways. Military aircraft operate across the region. Naval vessels transit the strait. Governments conduct exercises and prepare scenarios they hope never occur. Behind every headline sits the same uncomfortable calculation. A severe disruption would damage all sides. China depends on imported semiconductor technology. American companies depend on Asian manufacturing. Taiwan's economy depends on global trade. The chip network is sometimes described as a silicon shield, the idea that Taiwan's importance discourages conflict because destroying its fabs would impose catastrophic economic costs. But a shield made of supply chains is not invincible. A blockade, power failure, cyber attack, earthquake, or prolonged interruption could harm production without a single factory being physically destroyed. So the United States is attempting something that would have sounded improbable a decade ago, paying to bring leading-edge manufacturing back to American soil. In Arizona, TSMC's first fab entered high-volume production in late 2024. The company has announced plans that could raise its total American investment to $165 billion, including additional fabs, advanced packaging facilities, and a research center. The United States finalized up to $6 billion in direct CHIPS Act support for the project. The ambition is enormous. Create a second center of advanced manufacturing capable of supporting American AI, smartphones, and high-performance computing. But Arizona also reveals how difficult duplication really is. A fab is not an isolated building. It needs equipment technicians, chemical suppliers, construction specialists, experienced managers, stable utilities, packaging capacity, and an engineering culture that solves problems at any hour. Taiwan developed this ecosystem over decades. Rebuilding it across an ocean means moving not only machines, but habits, suppliers, and human knowledge. There's also a race against time. TSMC continues advancing in Taiwan while overseas sites expand. Its 2-nanometer technology entered high-volume manufacturing in Taiwan in late 2025, with more advanced variants following. A factory abroad can reduce risk and still remain behind the company's most advanced home-based capability. The goal, therefore, may not be complete independence. That would be extraordinarily expensive and perhaps impossible. The more realistic goal is resilience. Enough geographic diversity that one disaster does not freeze the entire system. Japan is building new capacity. Europe is supporting additional fabs. The United States is creating incentives. Samsung and Intel are fighting for advanced manufacturing customers. China is investing heavily in its own semiconductor supply chain. This is no longer a normal corporate competition. It is an industrial contest measured in decades. Engineering talent, energy, water, subsidies, and political patience. And TSMC is caught at the center. If it expands abroad too slowly, customers and governments fear concentration risk. If it moves its best technology abroad too quickly, Taiwan fears losing part of its strategic advantage. If it serves one market, another may impose restrictions. Every factory is now both a business decision and a geopolitical signal. For investors, the opportunity is obvious. AI demand is driving extraordinary appetite for advanced manufacturing. But the risks are equally unusual. TSMC must spend tens of billions before demand is certain, manage projects across different cultures and cost structures, and remain neutral in a technology conflict that increasingly demands sides. The company's greatest strength, being indispensable, is also its greatest vulnerability. Morris Chang built TSMC so chip designers would not need their own factories. Nearly 4 decades later, the world is discovering the price of that success. Companies escaped the burden of manufacturing, but the burden did not disappear. It became concentrated inside a small number of facilities, suppliers, and engineers. Somewhere in a clean room, a wafer is moving through hundreds of steps. On it may be the processor for a future phone, an autonomous machine, a medical system, or the next generation of artificial intelligence. The product is microscopic. The consequences are global. The next great technology war may not be decided by the company with the best chatbot or the loudest launch event. It may be decided by who can reliably manufacture the future and whether the world can keep those factories running when the pressure finally arrives.